Hi, my dear friends, welcome back to our YouTube channel. This is ADC Maths. In this class, we are going to define what is meant by quadratic form. Quadratic means degree 2, isn't it? Quadratic equation, quadratic polynomial, the same thing here. Quadratic form. At the same time, let us express the given quadratic form into the matrix form. So there is a exact the definition of the quadratic form, how to convert into the matrix form. So first of all, what is meant by quadratic form? Any homogeneous. What is meant by homogeneous? Homogeneous means in the expression each and every term have the equal degree, equal power. For example, if we consider x plus y whole square, what is x plus y whole square? Is equal to x square plus y square plus 2xy. So what's the degree of the first term? 2. Degree of the second term is 2. A third one is also 1 plus 1, 2. So it has the equal. This is called the homogeneous. Any homogeneous polynomial of degree 2. So degree 2 means quadratic in any number of variables. 2 variables, 3 variables, 4 variables. Yeah. Can we write what is a plus b plus c whole square? Yeah. A plus b plus c to the whole square is equal to a square plus b square plus c square plus 2ab plus 2bc plus 2ca. So this is also an example for quadratic polynomial. That is quadratic form in 3 variables. This is in 2 variables. This is in 3 variables. Now this is represented by the letter capital Q. It can be rewrite in terms of the matrix form x transpose A into x. What about x? X is the column matrix. X is the variable matrix, column matrix, x1, x2, etc., xn. Suppose there are n variables. Suppose there are 2 variables, then x is x1. And in this example, x is equal to a, b, c, 3 variables. So likewise, if there are n variables, then it is x1, x2, etc., xn. What about A? A is the real symmetric matrix. A is the real symmetric matrix because we are going to convert the quadratic form into the canonical form by using orthogonal transformation. You know the separate video I made for diagonalization of a real symmetric matrix. So I am going to use the diagonal matrix to convert quadratic form into the canonical form. Okay. That time the matrix A must be a real symmetric matrix. So here A is the real symmetric matrix. When we say that the matrix is symmetric, that means that Aij is equal to Aji, otherwise A equal to A transpose. Isn't it right? What about I and J? I and J represents the number of rows and number of columns. For example, let us say that if we consider Q is equal to x1 squared plus 2x2 squared minus 3x3 squared plus 4x1 x2 minus 6x1 x3 plus 8x2 x3. So this is the quadratic form. See that the degree is 2, degree 2, degree 2, 1 plus 1 2, 1 plus 1 2, 1 plus 1 2. So it is homogeneous of degree 2. So this is known as the homogeneous polynomial of degree 2 with 3 unknowns x1, x2, x3. 3 variables x1, x2, x3. So this Q can be written as Q of x1, x2, x3. So what about this case? In this case, x is the variable column matrix, x1, x2, x3. Now what about the A? A is the real symmetric matrix. So how to construct or how to find the real symmetric matrix from the given quadratic form? There's some separate template was there. What is it? Very simple. First of all, fill up the diagonals. The diagonals are nothing but the coefficients of x1 squared, x2 squared, the x3 squared. First one, second variable, third variable. Coefficient of x1 squared is 1. Coefficient of x2 squared is plus 2. Coefficient of x3 squared is minus 3. It's the diagonal wise. It's symmetric. Symmetric means Aij equal to Aji. Aij equal to Aji. So what about 1, 2? So 1, 2 comes here. You see that? x1, x2, x3, x1, x2, x3. So where we get x1 squared? In the diagonal only. x1 into x1, x1 square. x2 into x2, x2 square. x3 into x3, x3 square. That's why we pick up the coefficients of x1 square, x2 square, x3 square in the diagonal only. Now what about this term x1 and x2? Right? x1 and x2, but it is symmetric matrix. So what about x2, x1? So I think so these two places are same. So let us consider the coefficient of x1, x2, half of it. Why we can divide by half? Because it is symmetric. It is 2 times repeated. So we divide by 2. So what's the coefficient of x1, x2? It is 4. So what is the coefficient of x1, x2? Divide by 2. So that is 4 by 2, 2. So 2, 2. Right? And what about this one? x1, x3. Here also we get x1, x3. So these two terms, because of symmetricity. So coefficient of x1, x3. What's the coefficient of x1, x3? 6, minus 6. So what's the half of minus 6? Minus 3. So minus 3, minus 3. Right? Now what about this place? What about this place? The triangular place. This place being back x2, x3, x3, x2. See that? 2, 3, 3, 2. 2, 3, 3, 2. Both are same because of this symmetric matrix. So let us consider the coefficient of x2, x3 and the coefficient of x2, x3. Divide by 2 because it is repeated twice. So it is repeated twice. Let us see that this is the positions of the values from the given quadratic form. So what about the coefficient of x2, x3? It is 8. So what is the half of the 8? It is 4. So it is 4, 4. So once I repeat this, the diagonal wise coefficient of x1 squared, x2 squared, x3 squared, and this is x1, x2. So consider the coefficient of x1, x2, divide by 2, fill it up here because 1, 2 is equal to 2, 1 by using the symmetricity definition. And what about 1, 3? 1, 3 is here, so 1, 3 is here. And this is 2 and 3. So this is known as the symmetric matrix. So symmetric matrix. Let us see the examples. This is the x plus 1 whole square. So this is the given quadratic form of two variables. What about x? X equal to xy. What about the symmetric matrix A? What is symmetric matrix A? Yeah, once again, fill up the coefficients of x square. So here x, here xy, right? X into x square. So coefficient of x square is 1. Coefficient of y square is 1. So this comes to the denominator. That is the diagonal wise. What about the coefficient of xy? It is 2y. It is 2xy. So let us divide this 2 by 2. We get 1, 1. So we get xy. 2y is the time because of this symmetricity. Right? Now what about the a plus b plus c whole square is equal to a square plus b square plus c square plus 2ab plus 2bc plus 2ca. Now what's the corresponding? A matrix. Let's see that A, B, C. Right? Here A, B, C. A into A square. The coefficient of A square is 1. B into B square. The coefficient of B square is 1. C into C. The coefficient of C square is 1. So when we will get AB. So twice the time. Symmetricity. So coefficient of AB is 2. 2 by 2. 1, 1. What is the BC? Where we get BC? B into C here. B into C here. The coefficient of BC is 2. 2 by 2 is 1. So like that. Finally, where we get A into C, AC, and A into C, AC. So the coefficient of CA and AC is 2. So 1 into 1. So this is the way to get the corresponding symmetric matrix from the given real, that is quadratic form Q. Let us see some more examples. Let us see some more very interesting examples. This is the given quadratic form. It is Q. Here the variables are x, y, z. Here the variables are x, y, z. Is right? Is in terms of x, y, z. So there are three variables. Yes, right? Is x, y, z. Now, what is the corresponding real symmetric matrix A? Yeah, how will write this one? So here the row wise x, y, z, the column wise x, y, z. So what about the diagonal elements? It is x into x squared. So fill up the squares. X squared coefficient 6, y squared 3, and z into z squared is 3. Is right? Then next, find out the coefficient of xy. It is minus 4. So where we get xy, x into y, here also x into y. So these two places, let us fill up the half of the coefficient of xy. So minus 4 by 2 is minus 2. Minus 2. Is right? And what about this one? So this is yz now. What's the yz? Where we get yz? Y into z, y into zz. So these two places, I am going to fill it up by the coefficients of yz. The coefficient of yz is minus 2. So let's divide by 2, we get minus 1, minus 1. And finally we have xz. xz, the coefficient of xz is 4, half of that is 2. So this is the corresponding real symmetric matrix. Let us see that real symmetric matrix for this one. And what about x here? X will be the variable column matrix x, y, z. And similarly, in this second example, minus x squared plus y squared plus 4yz plus 4xz. So what's the corresponding A? What's the corresponding the real symmetric matrix? Once again, there are three variables. This is the three variables. Q is equal to x, y and z. Is right? So what's the corresponding A? The same idea. Let us go for the matrix, 3 by 3 matrix. First, the coefficient of x squared is minus 1, coefficient of y squared is 1, and there is no z squared, so 0. Right? So this is x, this is y, this is z. This is x, this is y, this is z. What about this term? X into y, x into y. There are no xy term, that means it is 0, 0. What about the yz? Yz, where we get yz? Y into z here and y into z. So these two places by yz. So what's the coefficient of yz? 4. So 4 by 2 is 2. So 2. And finally, this will give xz. This will give xz. The coefficient of zx is 4. So 4 by 2 is 2. Right? So this once again is symmetric matrix. What about the reverse process? Suppose when we have the real symmetric matrix A, what is the corresponding quadratic form Q? If we assume that x transpose AX by the definition, what about the x here? Suppose when we assume that x is equal to x1, x2, x3. So what about the x transpose? So x transpose is x1, x2, x3, and the A matrix here x1, x2, x3. Is right? Now what's the A matrix here? It is given that 8, minus 6, 2, minus 6, 7, minus 4, 2, minus 4, 3. So this is the given A matrix. This is the given A matrix. Let us convert or let us write the equivalent quadratic form. Let us write the equivalent quadratic form. For this, it is very easy one. Q is equal to, this diagonals will give the x1 squared, x2 squared, x3 squared. So it is 8 x1 squared plus 7 x2 squared plus 3 x3 squared. Is right? So x1 into x1, 8, x2 into x2, 7, x3 into x3 is 3. What about the coefficient of x1, x2? It is minus 6. So minus 6, minus 12 x1, x2. What about this place? x1, x3. x1, x3. This is also x1, x3. The coefficient of x1, x3 is 2. So 2 plus 2, 4. So we get 4 x1, x3. And finally, what about this term? There is x2, x3. This is also x2, x3. This is the coefficient of x2, x3. Minus 4, minus 4. This gives minus 8 x2, x3. So this is the way to convert from the given quadratic form into the corresponding real symmetric matrix, or the reverse process from the real symmetric matrix to the quadratic form. Do you understand? So I hope everyone is understand this concept. What is quadratic form? Any homogeneous polynomial of degree 2 with any number of variables is called the quadratic form. And this quadratic form can be written as x transpose AX. X represents the column variable matrix and A represents the real symmetric matrix. So how to convert from the quadratic form into the real symmetric matrix and from the real symmetric matrix into the quadratic form? That is the case. Very simple. The diagonal sum of the squares, that is this coefficients of first variable, second variable, third variable squares term, and the coefficients, half of the coefficients of the places x1, x2 or xy, xy, yz, yz, then xz, xz. So this is the symmetricity. This will indicate the symmetricity. See that symmetricity, right? That's why this is called the real symmetric matrix, because once we have this type of real symmetric matrix, then only we can apply the orthogonal transformation by transforming into the diagonal form. From the diagonal form, let us extend some more. This quadratic form can be rewrite into the canonical form. So this separate video I made for canonical form, how to convert from the quadratic form into the canonical form by using orthogonal transformations. Please go and watch our YouTube channel. Please subscribe so that you will get the notification whenever the new videos can be uploaded in our YouTube channel ADC Max. Thank you. Thank you so much for watching our YouTube channel ADC Max. Signing off, ADC. Thank you.